To support the United States Coast Guard in its mission of maritime domain awareness, our team developed a test platform for studying the vulnerability of marine navigation systems to electromagnetic pulse and geomagnetic disturbances. We concentrated on devices from the Coast Guard's Aids to Navigation, or ATON, network, which includes range lights and buoys along coastal waterways. The electromagnetic phenomena of interest have a number of sources, representing both artificial malicious threats and natural events. For instance, solar flares can lead to geomagnetic disturbances that affect the power grid. The phenomena that cause these problems were not practical or safe to recreate in the lab, but replicating one of their effects, unwanted currents coupled onto the power leads of an electrical system, was both feasible given our space, time, and budget constraints, and relevant to improving our understanding of the ways that these systems are vulnerable. This block diagram represents our setup: the power supply for the device under test, the signal generator used to generate a sinusoidal disturbance, and the oscilloscope used to measure both the magnitude of the disturbance induced and the relevant voltages on the device under test were all standard benchtop models common to UConn's ECE laboratories. The Line Impedance Stabilization Network, or LISN, protects the power supply from the induced disturbances and allows for the measurement of noise. We implemented the LISN first as a breadboard prototype, then as a PCB design. Using a simple resistive load as the device under test, we verified that the platform was capable of inducing the desired sinusoidal disturbances. However, we found that the gain is not the same at every frequency. While the output approximately equals the input between 100 Hz and 10 kHz, it's noticeably lower outside this range. Choosing a few widely separated frequencies gives us a rough idea of how the system performs under a broad range of inputs after taking only a few measurements, though more complete characterization would involve measurements at more frequencies. Before carrying out tests on the Coast Guard's ATON devices, we did so on the simple circuit shown below, the Mark I. This offered a number of advantages as a first device for testing, not least of which was that the Mark I's simplicity and inexpensive components meant that if an early iteration of testing proved destructive, replacing a Mark I was easier than replacing a Coast Guard range light array. When power is supplied to the Mark I, its two LEDs blink on and off successively. We measured the voltage across one of these LEDs as a function of time for 10 different levels of disturbance amplitude at 5 different frequencies, as well as taking measurements in the absence of a disturbance. Disturbances caused changes to both the period of the LED's on-off cycle and its duty cycle, or the amount of time that it was lit up during a given period. By comparing the values of these parameters for the disturbed and undisturbed devices, we can characterize system performance. These two tables chart these changes. Each value in the top table represents the percent difference in LED period length between the undisturbed Mark I and a device subject to a particular disturbance, and the bottom table charts similar percent differences in the duty cycle. Each column in the table represents a different disturbance amplitude, and each row represents a different frequency. Unfortunately, restricted lab access meant that we were able to conduct this quantitative testing and analysis on the Mark I circuit, but not the actual ATON devices. Testing of the range lights was more exploratory, revealing that the test setup required a power amplifier for those devices because of their current requirements. After adding the amplifier, the range lights demonstrated vulnerability to disturbances. By verifying that the test platform is capable of introducing the type of disturbances we want to create into the equipment under test, and by documenting the effects of these disturbances as functions of both the amplitude and frequency of the disturbance, this test platform and methodology provide a framework to explore the susceptibility of electronic systems to electromagnetic interference.